In our last video, you got a chance to be introduced to the idea of using an icebox problem to solve equilibrium questions. And in that, we used it to solve the KEQ, which is one way that we can use an icebox, but it's much more common that you're going to be using an icebox to solve equilibrium concentrations after being given initial concentrations in a KEQ. And that's what I'm going to show you in this video. In order to do this, I want to show you an example, and we're going to work our way through it so that you can see how to solve one of these problems. So this is the example we're going to work through. We are initially dealing with a concentration of H2 and I2 of 0.200 molarity. It tells us our equation there, H2 plus I2 produces 2HI, and we have to calculate the equilibrium concentrations knowing that KEQ is 64.0. So let's take a look at how we would actually do this. Like most chemistry problems, we start with a balanced equation. So we're going to take H2 and remember to include your states, because our states are really important when we're dealing with equilibrium. So H2 plus I2, both as gases, those are going to be in equilibrium with 2HI as a gas. Now this question, you were given the actual balanced equation, but keep in mind it may not necessarily be balanced. That's one of the biggest mistakes, is forgetting to balance that equation, because that's going to affect your coefficients later on. From there, we're going to create our icebox. So we're going to create a table giving a column for each of the substances, and then we're going to use this to help us solve our final concentrations. I'm just going to straighten this line out. There we go. Okay, so remember, we want a row for I, a row for C, and a row for E. So initial change equilibrium. You may sometimes actually see people write this as a rice box, meaning reaction, initial, change, equilibrium. I like to write my KEQ up here, just as habit, so that I know what it is and I know where to find it. But that's totally up to you. Whatever helps you solve this, go for it. So now we need to create a row for each of these substances. And then we need to fill in our icebox with the information that we know. So if we read through our question, it tells us initially the reaction has concentrations of 0.200 molarity for both H2 and I2. The other thing that we can infer is that this concentration was 0 molarity. Because it's a product and it didn't tell us what we were starting with, products, they haven't been formed yet, so their initial concentrations should be 0. The other thing that we know is that the reactants have to decrease and the products have to go up. If it's at 0, it has to go up from there to make something. And in order to make that, we have to lose some of the reactants, and we don't know how much, but we do know it's by some factor that we'll call x, and that's related to the coefficient for H2. So its coefficient is 1, so we have a coefficient of 1 here. Same thing here, same coefficient, same factor of decrease. But here we have a coefficient of 2, so it's going to increase by a factor of 2x. So that means at equilibrium, our concentration is where we started plus how much it changed, and that gives us where we are at equilibrium. So for HI, that's just going to be 2x. 0 plus 2x is 2x. But for H2 and I2, we're going to have 0.200 minus x. And it's going to be that for both of them. Now, I should mention here, it's also really important that you use concentrations in your icebox. The reason why is we're eventually going to be using our KEQ, and KEQ relies on you using molarity. So you must have numbers in molarity So if you have them in moles or grams or anything else, you need to change them before you do anything else. So now that we have that, what we're going to do next is actually solve these concentrations. We don't know what numbers they are, but we know a variable that we can use to help us solve them. We also know the number value for KEQ. By the time we use all that information, the only variable left is going to be X. And since it's all the same variable, we can actually solve what that is. And once we know what it is, we can calculate our concentrations. So what we're going to do next is set up our KEQ. And remember, KEQ is the concentration of products, in this case HI, raised to the power of their coefficients. So HI has a coefficient of 2, so we need to square the concentration of HI. That's going to be divided by the concentration of reactants, so H2 multiplied by I2. Please keep in mind here too, this is dependent on the states. So solids and liquids don't go in KEQ, but aqueous and gases do. So now that we know our KEQ and we know all this information, we can actually plug in those equilibrium values into our equation. The other thing we can plug in is the actual value of KEQ. So KEQ has a value of 64.0. So we can plug that number in. And HI has a concentration of 2x once it reaches equilibrium. The equation tells us we need to square that value, so it's going to be 2x squared. Now, the other thing we are going to do here is fill in our concentration of reactants. So the concentration of H2 at equilibrium is 0.200 minus x. The concentration of I2 is the same thing. So 0.200 minus x. At this point, what I'm going to do is rewrite this, because 0.200 minus x multiplied by 0.200 minus x, well, another way to write that would be to write 0.200 minus x squared. Because it's the same thing, we can multiply them by each other, and another way we can rewrite them as squared. And what that also leaves us with on the top is 2x squared, and that's all equal to 64.0. Whenever on the same side of an equation you have a squared on the top and a squared on the bottom, you can then take the square root. And if we take the square root on one side of an equation, we must take the square root on the other. Anytime you do something on one side of the equation, you must do it on the other to keep it equal. The reason we're taking the square root is to get rid of these squares. And what that's going to do for us is allow us to calculate the actual concentrations by figuring out what x is. So the square root of 64.0, well, that's going to be 8.00. I'm keeping 2 decimal places to preserve significant figures. There's 3 significant figures here. I want to keep that in mind as I continue my calculations. So I have 3 significant figures here. On the right-hand side, taking that square root eliminates those squares. So now we have 2x on the top of our equation, and we have 0.200 minus x on the bottom. So now all we're going to do, I'm just going to move this down so we can see, is we're just going to do some algebra. So we're going to actually just solve x by working through this. So our first step here is we want to multiply both sides by 0.200 minus x. That's going to help us by canceling out this on this side and getting rid of that denominator. So what that's going to do now is on the right-hand side of the equation, all we have left is 2x. We've eliminated the denominator, and now it's over on this side. And so we're left with 8.00 multiplied by 0.200 minus x. So now we're going to distribute into the brackets. 8.00 multiplied by x, that's going to be 8.00x. 8.00 multiplied by 0.200, that's going to be 1.60, and that's still equal to 2x. Now we want to solve by getting x on both sides. So the terms that have x, we need to move them to the same sides of the equation. Since this is a negative 8.0, we're going to add 8.0x to both sides of the equation. That's going to eliminate 8.0 from this side of the equation. All we're left with on the left is 1.60. And 2x plus 8.0x, that's going to be 10.00x. Now to solve, we're going to divide by 10.00x, or just 10.00. If you do it on one side, you have to do it on the other. That's going to cancel out 10. And all we're going to be left with is x. And x here is going to come out to be 0.160. So we've done all this work to find out that x is 0.160. You may think that we've already finished, but we're actually not done yet because this is just x. The question is, what are the equilibrium concentrations? So we need to jump back up to the top, and I'm just going to write x over on the side so we don't forget what it was since it's out of frame. It was 0.160. And now that we know what x is, we can actually calculate these concentrations. So the concentration of HI is going to be 2 multiplied by x. That's going to be 2 multiplied by 0.160. The concentration of HI is then going to be 0.320, and don't forget units. This is a concentration, so the units are molarity. So that is my equilibrium concentration of HI. But we still need to find out the H2 and the I2, and they're going to be the same values. So the concentration of H2 is going to be equal to the concentration of I2, and that's going to be equal to 0.200 minus x, and we already solved what x is. X is 0.160. So the concentration of those two is going to be 0.040 molarity. So that's my concentration of H2. And that's also my concentration of I2. So there we have solved our equilibrium concentrations. Now, after all of this work, you may think it would be nice to know if I actually did it right. And luckily, there is a way that we can actually check to see if we've done the work properly at this point. And that is to take the concentrations that we solved, plug them into our KEQ equation, and if we did it right, they should equal what KEQ is. So let's try that and see if we got the right answer. So we're going to jump down to the bottom here, and we're going to do a little check. To do this, we're going to plug our values into KEQ. Remember, it's HI squared divided by H2 multiplied by I2. So we calculated what all these numbers were. We're going to plug them in. So 0.320 squared divided by, and I'm just going to write this as 0.040 squared. Hopefully you can see why based on what we did before. KEQ is going to come out to be 64. That means that we did this right. Because KEQ is actually 64, and when we plug these numbers into the equation, it gives us 64, it means that we've calculated the right answer. I should mention with this check, if you round these numbers off, it will push you further away from the actual KEQ. So if you're doing your check, try to put unrounded numbers before significant figures to see if that gives you a little bit closer value. But that is ultimately how we solve a problem when we need to know equilibrium concentrations, knowing only initial concentrations. Set up your reaction and balance it. Set up your icebox and make sure to apply coefficients. Plug your equilibrium values into the KEQ expression. That's the chemistry portion. The rest is algebra and math. Once you solve for x, plug x into your equilibrium concentrations. Check your answer by seeing if it gives you your KEQ. And it should be how you solve an icebox problem. So thanks for watching. I hope this helps you understand how to work with icebox problems a little bit more. And I'll see you in our next video as we start talking about KSP.